Hello, everyone. Thank you for joining us. We are going to dive right in today as we do have a fairly extensive agenda with lots of good information. So let's dive in. If we go to the next slide, please. So we do have 4 panelists who will be giving presentations today. Just the usual disclaimers that these views are related to our panelists and are not necessarily those of the Ethernet Alliance as a whole, but they are here for your information. So this webinar is webinar number 2 in a 3-part series. Our first webinar was Ethernet in the Field, which targeted 50G per lane rates. That is now available on demand. Today we are doing our Ethernet in Design, looking at our 100 gig per lane rates, and then the next one, which will be upcoming, is Ethernet in the Future, looking beyond what we have now and looking at our 200 gigabit per lane technologies. So my name is Kay Doobie. I am the Ethernet Operations Manager and Strategic Operations Lead at the UNH Interoperability Lab. I'll be our moderator today. We will have a Q&A portion at the end of this webinar, so please feel free to add your questions to the chat and we'll have those ready for the panelists when we wrap up. So just a couple of brief slides about the Ethernet Alliance for those who are unfamiliar. We are a global community for the end users of products, those who design the products, as well as academia and those who research and develop technologies. We're here to really promote this industry awareness and acceptance of the products that are there, both with the current IEEE standards, as well as getting involved in those that are up and coming. We really want to make sure that our customers, both the ones who use our products in the end and those who use the standard and the technology as well, are able to quickly move into industry and move into the market. And then we want to be able to provide resources just like this webinar to provide education and to demonstrate more multi-vendor interoperability. And then just a couple of key points from our strategy before we dive into the technology. We are here to help provide that interoperability and testing and assurance. We'll hear a little bit more about that from Pavel later on. We do want to make sure that everybody is able to work together, as well as host these types of webinars to provide information for everybody. And then one other way that we can help the industry is by continuing to promote at various events. So we do have the Ethernet Alliance, the roadmap, and looking forward for what's going on in the future. So this is available both online, and we do have the availability to pick up or to get access to some equipment that you can use at events like the OFCs or other available events throughout the year. So from here, we're going to dive into our first presentation with Nathan Tracy. So he'll be going over how Ethernet is enabling the next generation, looking at our 100 gigabit per second lane rate. Take it away, Nathan.
Thank you very much, Kay, and thank you all for joining us today. So I'll just take a few minutes of your time and talk about how IEEE and the Ethernet are enabling this next generation 100 gigabit lane rate. Next slide, please. So some of the various 100 gigabit per second lane rate enablers that have become available to the industry are listed here. So 802, IEEE 802.3 Ethernet standard has developed a number of new clauses that enable and promote 100 gigabit per second signaling to meet next generation networking needs. And so first of all is 802.3 CK, and this is the clause or the extension to the standard that we'll spend a lot of time talking about today. So I'm going to come back to that on my next slides, but just to set the stage on some of the other activities, 802.3 CT establishes the DWDM specifications for applications with a reach of 80 kilometers that support DWDM. 802.3 CU is a project that has now been published, and it establishes single mode 100 gigabit per second wavelength optical specifications and various options. And those include 100 gigabit base DR, which is a 2 meter to 200 meter specification, 100G base FR1, which is 2 meters to 2 kilometers, and then finally 100G base LR1, which is 2 meters to 10 kilometers. And then for 400 gigabits base FR4, so this is 4 lanes at 100 gigabits each, we have 2 meters to 2 kilometers, and we also have 400G base LR4-6, which is a longer reach 2 meter to 6 kilometer solution, and both of those are based on CWDM technology. And then finally, filling out the portfolio, 802.3 dB establishes multi-mode short reach optical specifications. And those include 100G base VR1, 200G base VR2, 400G base VR4. And these are over 1, 2, or 4 pairs of multimode fiber, a reach up to 30 meters on OM3, 50 meters on OM4, and 50 meters on OM5. And then finally, slightly longer reach is 100G base SR1, 200G base SR2, and 400G base SR4 over 1, 2, or 4 pairs of multimode fiber. And in this case, the reaches are 60 meters on OM3, 100 meters on OM4, and 100 meters on OM5. So you kind of see the pattern here. We've established various different technical solutions that leverage 100 gigabit per second per lane, and then we're using those for both enabling 100 gig, 200 gig, and 400 gig. So now I'll take a deeper dive into 802.3 CK, and if we could go to the next slide. Okay, so 802.3 CK establishes the 100 gigabit per second lane rate electrical interface specifications. So these are all based on PAM4 signaling modulation, and it defines solutions again for 100 gig, 200 gigabits per second, which is based on 2 lanes of 100 gig, and then 400 gigabits per second based on 4 lanes of 100 gig. The Reed-Solomon FEC is applied for all of these solutions and all of the different links that are specified in the CK standard. And the electrical specifications that are addressed are chip to chip. And again, you see the pattern here. Oh, I see a typo on my slide. Okay, so you see the pattern where in the case of chip to chip, we do 100 gig AUI-1 chip to chip. So it's the 1 indicates it's a single lane of 100 gig. And then you come to the typo where it says 100 gig AUI-2 chip to chip. That should be 200 gig AUI-2 chip to chip. And then 400 gig AUI-4 chip to chip. And there you see in the far right column, it's spelled out very simply: 1 by 100 gig, 2 by 100 gig, and 4 by 100 gig. So the next interface that's specified is chip to module. So this is a very well-known, well-established interface that's used in industry to get from the switching function within a switch out to the pluggable modules or copper cables that might be out there. So in the case of optics, it's a chip to module spec. And again, the same pattern of 100 gig AUI-1, 200 gig AUI-2, and 400 gig AUI-4. And the same clarification on the far right showing 1 by 100, 2 by 100, and 4 by 100. The next link that's specified in CK is copper cable. And again, you see 100 gig, 200 gig, 400 gig, and then finally backplane, which follows the same pattern of defining 100 gig, another typo, 200 gig KR2, and another typo, 400 gig base KR4. So we'll get those slides corrected before we post the slide deck. But now you kind of understand the basic framework of the CK specification. Next slide, please. So first, a couple words on chip-to-chip and chip-to-module. So the chip-to-chip interface, which is abbreviated as C2C, enables approximately 25 centimeters of reach with conventional PCB traces. And this is based on the recommended 20 dB max channel loss. So of course, the primary specification is the amount of loss, not the amount of reach. And I show on the far right side of the slide where the yellow arrow indicates, a link potentially from one chip to another chip. This is the type of application that we're addressing with the chip-to-chip clause. And now moving down to chip-to-module, abbreviated C2M. So this is enabling the classic pluggable optical transceiver architecture. The overall channel loss is 16 dB, and the host loss allocation is up to 11.9 dB. And in the graphic that we show on the bottom of the slide, so this is snipped right from the 802.3 CK specification, and it shows how we allocate the loss parameters to make up that total 16 dB. So you see that we've allocated 11.9 to the host, 1.6 dB to the connector, and 2.5 dB to the module. And on the far right side, I've inserted some graphics that give an idea. So in the middle of the far right side, that graphic shows a switch silicon device in the center of a switch enclosure where you don't see any cabling or anything going out to the I/O panels because this is served with PCB traces. And then on the view on the bottom of the slide, you see a hybrid mix where some of the I/O ports on the face of the switch are served by PCB traces, but some of them might be served by copper cable. This is all allowed per the way that the specification has been written. Next slide, please. Okay, compliance test board methodology. So some other panelists will talk about this in greater detail today. And so my goal is just to provide an overview of how that works. But what we do is we take a look at from the transmit function on switch 1 and the receive function on switch 2, and we take a look at how we're going to allocate the losses and what are the different testable interfaces that are going to be part of this. And from that, we define test boards or compliance test boards, and that's what's shown on the far right side of the slide. So here we're showing in the top image an MCB or a mated compliance board connected to a cable assembly, which then has a mated compliance board on the other side. And so this gives us the testable interfaces to verify that a cable assembly is in compliance. The image below that is showing a host compliance module. So we have a host switch and we plug in a HCB or host compliance board to that. And that gives us a testable interface to verify that that host is in compliance. And then to the right of that, we show that the similar, we're using an HCB to check compliance of a second host. And then on the bottom of the slide, we're showing the mated MCB and HCB. And all of these specifications are included in the CK specification so that you understand what are the test points and what are the loss allocations for all of these different portions of the circuit. So this is what gives us the ability to do full compliance testing so that when hardware gets to the field, we know that it's going to work well. Next slide. So those same test vehicles are used for both optical modules as well as copper cables. And here on the far right side of the slide, I show a copper cable that is mated to 2 of those MCBs. And below that, I show a top-down view of the MCB. In this case, it's an OSFP MCB. So I'm talking about the copper cable interface, and this is really a critical industry building block for a couple different reasons. One, it's widely used by the marketplace due to its low power, also low latency. It does not have any E to O conversions or anything like that, as well as its low cost because it's a passive device. So a lot of the marketplace thinks about this from the standpoint of use copper where you can, use optics where you must. And so that's really why this is a critical element of the IEEE specification. Often used for switch to server links, but then there's also use cases in an aggregation switch matrix as well. And so, both of these are widely used. There's a number of form factors specified in 802.3 CK. One is SFP, which is a single channel, SFP DD, and DSFP, which are both 2-channel interfaces, QSFP, which is a 4-channel interface, and QSFP DD and OSFP, which are 8-channel interfaces. And so those are all described in the standard. And as I'll show on the next slide, what it does is it enables us to bring a broad flexibility to the marketplace in terms of the different interconnectivity options. The cable assembly loss in the standard is 19.75 dB at 26.5 gigahertz, which enables a cable reach of 2 meters. And separate from, as compared to the optical specification for copper cable, the host loss allocation is 6.875 dB. So it's a lower loss allocation for the host in the case of a copper cable, simply because it is a passive channel with a little bit higher loss. And I will note that already we're seeing 2nd-generation silicon coming to market, which is enabling longer cable reaches. So not surprisingly, and we've seen this in the past, as the industry advances, these loss objectives that we have in the standard are able to be surpassed. So the minimum spec initially was 2 meters. Now we're starting to see some testing up as high as 4 meter reaches. Next page, please. So this kind of gives an idea on how we use those different port types to enable this flexibility that I was describing. So for 100 gig CR1 application, SFP, which is a single electrical channel, one of transmit, one of receive, that enables a single port of 100 gig. But using SFP-DD or DSFP, you now have 2 ports of 100 gig in that single connector interface. And with QSFP, you see 4 ports of 100 gigabit that can all be supported with that at that 100 G base CR1 rate. And QSFP-DD or OSFP, being 8-channel devices, they can support 8 ports of 100 gig. So a lot of times folks say, oh, well, QSFP DD, that's a 400 gig solution or an 800 gig solution. It's not correct to simply think of things that way, and you need to understand what the use application is. As shown here, that QSFP DD might be being used for 8 ports of 100 gig. And then you see, as I go down the slide to 200 gig base CR2 or 400 G base CR4, you see how these ports now these connectors are used to enable lesser ports at 200 gigabits per second. So looking at the same example, QSFP-DD can support 4 ports of 200 gig, or in the case of 400 gig, that QSFP can support 2 ports of 400 gig. So you get an idea on how these port definitions can be used for different data rates. And then going to my last slide. Oh, I'm sorry, not my last slide, second to last. So backplane is also defined in the standard. And again, 100 gig, 200 gig, and 400 gig are defined. The max channel loss for backplane is 28 dB at 26.5 gigahertz. And that is a BGA ball to BGA ball specification. And then across the bottom of the slide, I simply showed some various backplane configurations that are currently being deployed at 100 gigabit per second, such as a conventional backplane, which uses PCB traces to run from line card to line card. Orthogonal backplane, where you see the rear switch fabric, which is directly plugged to all 6 of those IO cards. And then the cabled orthogonal midplane type of architecture. And then finally, to the far right, the cabled backplane structure, where cabling is used to connect all of the line cards together. Next slide. And this will be my summary. So the IEEE specifications are published, they're out there, they're available, and they are enabling electrical and optical interfaces over a wide range of media. And these products are now coming to market as at the same time they're in their development phase. This allows optimization of various implementations according to power, reach, or whatever the market demand might be, while at the same time benefiting from the IEEE plug-and-play, multi-source, fully interoperable type of interface. And just a note, and the other panelists will speak on this a little bit more. At 100 gigabits per second, the lane rate challenge, the lanes are actually quite challenging, and to a degree never before required. It requires careful attention to detail in order to bring these systems up. But the standards are there, they're published, and with that, I'll turn it back over to you, Kay.
Awesome. Thanks, Nathan. Great to see a nice overview of where we are in the industry. From here, I'm going to pass it off to Aditya to go over some hardware measurements.
Thank you, Kay. Hello, everyone. This is Aditya Muralidharan, Staff Applications Engineer in Intel Programmable Solutions Group. So in today's discussion, my focus area would be on the 100 gigabits per second lane rate hardware measurements. So in this particular topic, the demonstration results of the different Ethernet variants at 53 gigabaud or 100 gigabits per second per lane will be showed across multiple performance metrics. The first one would be the bit error rate performance, and we'll also go over the forward error correction or the FEC statistics. And there are some Ethernet packet and throughput tests, both for 400 and 800 gig solutions. And the measurements were made across different media types, such as channel evaluation board, direct attached copper, and optical fiber, including different form factors, both the QSFP, DD, and OSFP, which Nathan touched upon in the previous topic. Next slide, please. So in this topic, we'll have 3 focus areas. The first one would be the 802.3 CK electrical measurements, which will be predominantly focused on the PMA or the PHY layer. And the next 2, the 400 gig base CR4 and 800 gig GOI8, will be towards the layer 2, where the MAC is also involved. Can we go to the next slide, please? Yeah. So for 802.3K electrical measurement, the test setup that we have here is with an Agilex F-tile dev kit with a channel evaluation board. And we are using 106.25 gigabits per second PAM4 line rate and the QPRBS31 pattern. And the main idea of this testing is to increase the trace length ranging from 1.2 to 10 inches, which is basically a 28 dB end-to-end loss. And here, the form factor of the connector that is used between the dev kit and the channel evaluation board is a OSFP. Next slide, please. In terms of the channel model, right from left to the right, you could see the transmitter, which is the Agilex F-tile FHT transmitter. There is an OSFP to SMA adapter. We have an SMA cable and channel evaluation board. And similarly, on the RX side, the SMA cable, OSFP, SMA adapter, and the FHT receiver. And in terms of the dB loss, the F-tile FHT transceiver, the corresponding TX and RX dB loss, and OSFP to SMA adapter and SMA cable at Nyquist 26 gigahertz, the corresponding dB loss are captured on the left. And on the right, that's the channel evaluation board for different trace inch, starting from 1.2 inch till 10.7 inch. Next slide, please. So this table gives you the data from 1.2 inch to 9.5 inch, and the end-to-end insertion loss for the 106.25 gigahertz, starting from the 15 dB for 1.2 inch, which is the end-to-end loss, going down to 28 or close to 28 dB. And you could see the prefect BER for a smaller trace length, it's pretty low. And then as you increase the insertion loss, the bit error rate increases. And there is a point, insertion loss point, where the FEC correctable errors starts to kick in, which is towards the end around 28 dB mark, where your FEC is able to give you an extra margin. And here, the BER values were collected for 10 minutes after starting the transmission. So this slide gives you an understanding, like as you go on increasing the insertion loss, the BER increases, and the FEC portion comes into picture around the 28 dB mark. Next slide, please. So the next setup is the 400 gig base CR4. So here we have two F-tile Agilex dev kits, which is connected using a 1 meter DAC cable, which is in the QSFP-DD form factor. And the 400 gig here, Ethernet, which is hard IP, consists of 4 lanes, with each lane running at 106.25 gigabits per second. And the Reed-Solomon 544-514 forward error correction scheme is employed for this particular topology. Next slide, please. So the way to look at the hardware results is I've broken down into 2 different buckets, the PHY stats and the FEC stats. So things to monitor here is for both the boards, board 1 on the left and board 2 on the right. Here the PHY stats are in good condition, like the PCS ready, TX lane stable, DSKU status. And also, if you look at the bottom of the screen, have like 2 portions. One is the board 1 FEC stats and the board 2 FEC stats. And one of the important things to monitor here is the uncorrectable code words is 0. And in terms of the correctable code words, or correctable code words, you can see the FEC tail for this particular RS 544-514 FEC. This can correct 15 symbol errors per code word. And you could see for this particular setup that we have, the FEC is able to do that correction. And this is well within the range of the 15 symbol errors. And that's what the FEC tail is being highlighted in this particular slide set. Next slide, please. So here is an analysis of the MAC, the layer 2 statistics between both boards. And here, the random length packets were tested. When I mean random length, starting from a 65 byte till 1518, the packet generator that's part of the design, it sends random length packets, and correspondingly in the statistics column, we try to capture the packet type according to the length. And the thing that monitor here is the TX stats on board 1 matches with the RX stats on board 2, and similarly the TX stat on board 2 matches with the RX stats on board 1. So this is an confirmation that the design is working and the packets that are being transmitted and received are good. Next slide, please. So here, so this is the 800 gig GOI 8 test setup. So here, again, we are using the Agilex 7 FPGA I-Series development kit, and Ethernet 800 gig soft IP is being employed with 2 F-tiles, and with each F-tile having like 4 lanes of 100 gig transceivers, and then it's combined using an MXP cable jumper through QSFP-DD. And then we are using a 3 meter optical fiber to connect it with an 800 gig Ethernet protocol tester. And the optical module that's being used is the 800 gig DR8 module. And one of the main things to note here is in terms of the 800 gig, right now, as Nathan mentioned, the spec is conforming to the final draft. But here we are using the proof of concept, the soft IP solution, which is on the core of the FPGA. And then F-tile is basically using the PMA direct mode, which is the hard end as part of the logic. And then we are combining two F-tiles and then using a QSFP-DD form factor optical module to connect it with an Ethernet protocol tester. Next slide, please. So these are the hardware results from an FPGA standpoint. Again, here the PCS stats are in good condition, and then the FEC uncorrectable code words is 0. And another interesting thing that you can see is in terms of the graph, it gives you the throughput analysis between the transmit and the receive data. In this particular setup, we are sending the 1518 byte packet size, and the 100% throughput is achieved on both the transmit and the receive. The next slide, please. So here, this is from the tester side of things, and you can see the tester is showing the 800 gig link up status, and also the tester is running a full 100% throughput from the tester side, and both the transmit and receive are in good condition here. So overall, so this is my last slide. So overall, what we are trying to highlight here is with respect to the 100 gig per lane solution, we have this multiple form factors of OSFP, QSFP-DD, and also we have this 400 gig Ethernet and 800 gig Ethernet. And in this particular presentation, what we have highlighted is what are the different types of testing that can be done and how to monitor the data on your end. So thank you so much for giving this opportunity.
Awesome. Thank you, Aditya. From here, I'm going to pass it off to John to go over some system validation challenges at TP2, looking specifically at clause 162. So take it away, John.
All right. Thank you, Kay. Thank you, Aditya. We'll take it from, into the physical layer domain here a bit further and discuss some of the practical aspects of conducting TP2 related measurements. And for many people, this has been one of the more persistently difficult measurements to execute out of the IEEE 802.3 CK measurement portfolio. The couple of measurements I specifically wanted to drill into here are the JRMS J3U03, the conventional J3U in the EOJ calculation. These measurements have always been extremely tight, and even at by tight, I mean low margin. The standards process, even towards the end of the CK spec development process, was in the midst of working out some details on giving some additional margin here. And some changes were made to accommodate the higher loss requirements. With regards to the recommendations from the spec standpoint, if you do an additive assessment of all the losses that are allowed in a TP0 to TP2 sort of configuration, you come up to a recommended loss of 10.9 dB. In practice, however, we're seeing packages that have 512 SerDes in a package now, and the packages have gotten larger. And those larger packages have associated higher loss, and people have encountered issues with trying to satisfy TP2 and hit that 10.9 dB target. And in practice, sometimes people are seeing losses up into the 16 dB region. And this is one of the things that complicates these jitter calculations. The general guidance is that don't do a precision jitter measurement at the end of your channel. And we're violating that in this regard. We're basically doing a high precision jitter measurement at the end of a 10.9 to a 16 dB channel in practice. One of the changes I alluded to a moment ago was the introduction of the J3U03 measurement, which is a variation of the J3U calculation. Both of these are subclasses of the 12-edge jitter methodology that's defined in the IEEE spec. J3U has it's a measurement that basically does it's a glorified end cycle jitter measurement that uses precise locations in a PRBS 13Q pattern and it measures that pattern, the jitter, from one location in that pattern to the same bit sequence in the next pattern. And it works fine for 3-level transitions. 2-level transitions become a little bit dicey, and single-level transitions after you've gone through 16 dB of channel loss are very problematic. So the allowance that was made here was to incorporate the J3U03, give it the old J3U spec limit of 115 milliui, and then to push the actual spec limit for J3U up to 125 milliui. Next slide. In line with the discussion of channel loss, one of the things that has to be carefully considered here is the type of interconnects that get used for the mated test fixture. It's inescapable that you have to incorporate an HCB into this MCB form factor to get a mated test interface. And the electrical performance of this mated test fixture or mated test interface is defined in clause 162. And you can see here you're given a nominal reference for insertion loss, and then you're given a minimum and a maximum allowable window here for insertion loss. The minimum allowable is 4.8, the maximum is 9.13. You've got a pretty good spread there since the nominal is 6.6. As you can see in the graph in the upper right, this is an actual insertion loss of one of the test fixtures that we're talking about here that comes in at 6.9 dB. So it's walking right down the middle reference line. Not all fixtures are of this good a quality. And also remember, it's not just insertion loss, reflection. The SDD22 here is actually a really important element. You have to make sure that you're keeping your reflections down below 15 dB. Otherwise, you're going to have a lot of difficulty with resonance behaviors in your measurements. Next slide, Kay. So this is an illustration of sort of TP2 in the overall scheme of things here. TP0 is over here on the right-hand side of your transmit function. You go through an MDI and you wind up at the back end of the HCB, which is your TP2. And that's the red circle we have on the right-hand side of the mated test fixture in this illustration. Now, the measurements that are cited in clause 162, there's a variety of them. There's things like SNDR and RLM, and it states that these measurements have to be satisfied, the specifications have to be satisfied at precise presets, and there are 5 presets to be specific here. J3U, J3U03, EOJ, and JRMS are a little bit different, and you see the clause down there in clause 162.9.4.7, where it says the equalizer setting is chosen to minimize any or all of the jitter parameters. So the idea here is that you have the option to go above and beyond your typical 5-tap filter configuration on your transmit side to find a way to get a passing J3U number. And the whole idea of the transmit FFE here is to compensate for the channel loss. So you want to overcome that loss and provide as good a signal as you can possibly at TP2. You're not allowed to do any kind of reference receiver equalization on the receive side. You can't do a CTLE, you can't do a DFE, you can't do a few things on the receive side, but you can configure your transmit FFE. Again, you set up your transmit FFE to minimize your jitter numbers. This is all done with a 40 gigahertz 4th order Bessel-Thompson filter. And this is one of the filters that carries a relatively linear phase response out to, about 60 gigahertz to 59 gigahertz is where we track that phase response and how it contributes to the overall jitter calculation. Next slide, Ken. One of the things that's you'll encounter here is the eyes will be closed. At TP2, you're going to encounter a situation where the DDJ elements are actually quite high. And the eye diagram in the lower portion of the screen is a great example of what you would typically observe at TP2. eyes are completely closed. Now, the good thing is that the 12S jitter measurement methodology works pretty well, even under these conditions, because again, there really is no eye measurement in clause 162. There's an eye measurement in chip to module where we have to evaluate vertical eye closure, but there is not an eye to speak of in clause 162. We're required to measure jitter, and we can do that on a cycle-to-cycle basis by looking at the waveform, and the eye will be closed. In this illustration, you show the open eye above there. You can equalize the eye. You can apply a CTLE and additional equalization on the signal to clean it up. And this is really what you see when you remove the deterministic element from the signal. But in its own, the TP2 signal will have a tremendous amount of deterministic jitter. You can see here in the acquisition across the bottom trace, the kind of typical jitter numbers you would see in this case here, a J3U of 111 milli. It's actually pretty dang close to your spec limit, but it's passing in this case here. This is a existence proof that it can be done under the right conditions. Next slide. So, why is TP2 measurement use case that important? Well, if you think about it, the standpoint of a server is going to be an enclosed black box. The only thing that you have accessing that server is the QSFP or the OSFP slot in the back of the server. So the ability to insert a ACB and evaluate whether or not the electrical conformance is at spec limit at those test points is an important evaluation that people want to do with the systems in their data center, as well as for debug purposes. The key takeaway here is that TP2 is based on a conservative set of loss values, and typically you have to deal with slightly higher loss. This table down here in the lower right is an illustration that, with 8 dB of channel loss, which is unrealistically low, you'll notice that you can get by with just 4 taps of transmitter fur, and you get a set of J3U numbers and JRMS numbers that are actually well within spec with a lot of margin. But if you push the total loss up to 15 dB, you're fully employing all 5 taps of a TX fur. And if you incorporate additional reflections that would come about as a result of, hey, maybe having a marginal return loss, the tap count or the power in the taps will go up considerably. Very good. Next slide. So EOJ. EOJ has been problematic from day one. And one of the issues that's come about in EOJ is the fact that the unintended consequence of doubling the bit rate and keeping the pattern length constant is that we've brought the pattern harmonic of an even odd pattern back to back down to a pattern harmonic frequency of 3.24 megahertz. And that's basically in the band of the PLL tracking system. Now, that wouldn't normally be a problem, but you park the physical PLL that's being tracked on the receiver side at 4 megahertz. And if you're dealing with OIF specifications, which run a little bit faster, OIF specs run nominally 56 and 58 gigabaud, you push that pattern harmonic right up into the 4 megahertz PLL tracking location. So the hardware is tracking phase at 4 megahertz, and you start pushing the in-band pattern harmonic right into the PLL. You wind up with a slight bimodal distribution in your jitter calculation here. Now, you can actually see this also on a real-time scope as well. A real-time scope is not as sensitive to this because it has all of its clock recovery in DSP. But in a case where you actually have a physical clock recovery circuit, this can be problematic. Next slide. So what can you do about it? Again, it was recognized that this EOJ relationship with the 4 megahertz PLL was an unintended consequence of the bitrate doubling. And a few provisions were put into the specification to accommodate this. So number one, you can drive the loop bandwidth down. You can go down to a loop bandwidth of close to 1 megahertz is what the spec put in place. And also you can do a alternate pattern. The CK specification put a provision in here to support a PRBS 9Q. Now, a PRBS 9Q is a shorter pattern, so the pattern harmonic on this is going to be much higher frequency, and it is not being tracked by the PLL the way something would be if it's running right at 3.2 megahertz. Okay, next slide. Instrument calibration and correlation has been a long-standing objective here of the efforts of the EA, and to make sure that regardless of the instrumentation that gets used, you get the same answers or similar answers. And there are differences in answers that have architectural dependencies here. So I just wanted to walk through a couple of these differences. These two instruments that you see in front of you right here, the one on the right is a real-time scope. The one on the left is an equivalent time scope. The instrument on the right has an effective number of bits of about 5.5. The instrument on the left has an effective number of bits in excess of 6.5. So it's just again, an attribute of the architecture at work here. If you're trying to measure JRMS and affect random jitter components, there is no instrument that comes out better than a sampling platform because it has an ENOB advantage. And that's really where the ENOB advantage comes to play. It gives you the best fidelity and best sensitivity for measuring JRMS and indirectly J3U as well. So you'll see here on the table, the DCA comes in at 23 milli-UI, and the UXR is coming in at 24.8. That's entirely to be expected. The real-time scope is measuring a little bit more jitter than a sampling scope would be. Conversely, if you walk down to J3U, this is looking at total jitter. Now, do note that this number is this is a failing score, by the way. This is actually a non-conformant device. But in terms of getting consistent failure across two instruments, this is the kind of correlation you might expect. We're coming in at 170 milli-UI on a real-time platform, 160 milli-UI on the DCA. Again, entirely expected. Now, the next line is unexpected, and I want to talk about that. EOJ, as I indicated earlier, is a variation of a cycle-cycle jitter calculation. And real-time scope architecture is actually superior for measuring EOJ, both from a clock recovery standpoint and simply a time-based architecture standpoint. You typically see nominally smaller EOJ values on a real-time architecture than you would on an equivalent time system that requires physical clock recovery. So you see, this is the one example where real-time instruments will give you a superior answer to that off of a DC or an equivalent time scope. RLM, you're going to see very consistent behavior there. V sub F is also important, but that's actually more of a function of how current your calibration is. They should track dead on. And SNDR, again, to within the normal run-to-run variations, should be very similar across these two instruments. Very good. Next slide. So I wanted to close on a couple summary points here. I want to encourage everybody to come to the Ethernet Alliance workshops and really don't think of it as a place to bring your finished product. Designs that are in progress are really welcome at these sort of workshops. The best thing to enable the test and measurement community, as well as the ecosystem in general, is to bring a wide variety of products that are in various stages of development. And even if you don't have a full passing conformance suite, people at the workshop can help you figure out what's going haywire in your design. Many of the devices brought to the workshop have interesting things to look at. And we're always looking at ways to improve our test techniques and methodologies to provide more accurate results. And the kind of interesting products that people bring to us help advance that entire agenda. The final point I'll make is that IEEE 802.3 CK has some very tight margins, validation margins for a number of these key measurements. Don't think that you're required to pass all these measurements on a single class of instrumentation. A mix and match approach is perfectly acceptable. If you're getting passing scores on JRMS and EOJ, but you're failing, you're failing EOJ, try doing the measurement or calculation on a real-time architecture and see if it works better for you. Conversely, if you're getting JRMS numbers that are too high on a real-time architecture, consider trying to do them on a sampling architecture and see if it improves matters as well. And most of all, bring your concerns and issues to the EA. We have a forum of people and experts who discuss this and love to dive into these topics. So bring your problems to the EA and we'll be happy to talk about them. Thank you very much. And back over to you, Kay.
Awesome. Thanks, John. And definitely a good reminder to bring any questions as you see them or problems up with the EA, as well as if you do have any questions. We've got one more talk before we dive into our Q&A, so feel free to add those into the Q&A session. But before we dive into those questions, we are going to pass it for one more talk with Pavel to go kind of over the most recent plugfest event.
Hello, everyone, and thank you all previous presenters, and thank you, Kay, for moderating nicely. So we have a set of people coming to the plugfest. Let's look a little bit like what does that look like in detail and see what was the last plugfest about. So my name is Pavel Živný. I am a Tektronix high-speed serial data expert, but I have two roles at this plugfest. I'm also a co-chair of this plugfest, really the co-chair which is focused on physical layer. All right. So I will make sure that I clarify if there is a need to be specific. So let's start with the first slide here. So we had 18 member companies coming to the plugfest, and you see a picture at the bottom right of the slide. So in fact, 18 was about as much as we could easily fit. We could fit more. It would take some work, and we are hoping for that to happen in the future. But it was really well attended. So the interest in the industry, I think, is encouraging. The focus of this plugfest really was the AO2.3CK, and that's not always that clear. It's typical that we have more than one particular standard that is of concern to the industry, and then we would have several different things to test. I will look into that in a moment. The Ethernet Alliance is obviously for members. So you can join the Ethernet Alliance, and as a member of Ethernet Alliance, you have access to plugfest and other activities of the Alliance. For example, this presentation here is brought to you by Ethernet Alliance. But if you are only interested in a plugfest, then it's okay to contact Ethernet Alliance, and we can accommodate requests to join the plugfest as well, right? All right, I think the plugfests for the Ethernet Alliance are typically 1 a year or 2 a year. Because of the strong interest in this H1 or first half of 2023 plugfest, we are considering another one for second half of 2023. And I cannot imagine we wouldn't have more plugfests in 2024, so we strongly plan on that. Let's go to the next slide. All right. So one of the things we discussed at the plugfest organization meetings before the plugfest is what really has a strong interest and what will get a strong attendance. And the plugfest we had in H1, this was the list. So we had several other things, and they didn't come up quite with the same volume. One of the ideas behind the plugfest is that the data is confidential. So if you are coming in with a device which is immature, you are not interested in the industry knowing that your device is not quite ready. You are interested in getting the measurements done, getting the interoperability tested against other devices, but you want that data to be confidential. If you are the only person with a certain standard, then the utility and the confidentiality are less obvious. And so you probably want to be interested in the plugfest, and the plugfest will be less likely to offer that testing. So for those reasons, we focused on the AO2.3CK listed here, and we had a little bit so 100G per lane, a little bit interest in 50G and did a little bit of that as well. Let's look at the optical slide. Next slide, please. So the things which we typically test at 100G speed is both the single mode and multi-mode intensity modulation direct detect. So traditional optical signaling, meaning not coherent, okay? And that was also discussed, and at this time we did have fewer devices. So there were many optical systems, but we did not do extensive physical layer testing on them because that was not the main interest. I'm imagining that with the new flavors of multimode, this will be useful in the future. While we are on this slide, let me mention something that's obvious to half of you and not obvious to others. So when we say 100G, 800G, 50G, what does that really mean, right? Nathan listed out the speeds pretty nicely in the beginning of this presentation, but I'll repeat it here just as we start more on the physical layer here. 53 gigabaud Ethernet at PAM4 carries 100 gigabit per lane. So if you have 8 lanes, it's called 800G. If you have 4 lanes, you have 400G. 800G, for example, might not even be part of certain IEEE specifications. It's simply extending the 400G. In some cases, people might do the opposite. 200G, 100G, that's just one lane of 53 gigabaud at 100. For the physical layer crowd, it's very interesting what the basic frequency spectrum is. It dictates the bandwidth of the measurements that's required. So for that reason, we oftentimes use the term 53 gigabaud. At PAM4, 1 gigabaud, one baud carries 2 bits of info, and with a little bit of overhead, 53 gigabaud carries 100 giga of payload in the Ethernet standard. All right, so that's what we mean by 100 gig in these physical layer slides. So for those of you on the call who are interested in optical, please consider bringing optical devices for the next plugfest. Here we have a picture from the plugfest. So I have several stations on one slide. So, and then let's look at them. So on the left, the large picture, you can see 2 oscilloscope stations, or really several, 2 stations from, oscilloscope stations from 2 vendors. On the left is the Tektronix station with several oscilloscopes for measuring up to 2 simultaneous DUTs. And you can see there is a screen and some DUT setup, and one of the vendors with DUT who is measuring their characteristics. On the right, you can see previous speaker, John Calvin, my esteemed colleague here on the panel in the EA, and also on the plugfest, and also my competitor in as far as the products go for oscilloscope measurements. So John is standing close to the Keysight test station, where there are several setups also for measuring 100G DUTs and for several other things. So this is traditional setup. You can see that there is some level of confidentiality. Everybody knows who is measured, who is being measured, but you don't get to see the result. And that's really the way it's supposed to be at the plugfest. There is an NDA signed by all the attendees, and we will be both releasing every DUT data to the DUT vendor alone in all the detail. And also we will be summarizing the data in an anonymized way for the industry to see. So that anonymized report is one way the plugfest feeds back to the industry and lets everybody see what the problems are and what are the solutions which work fine. What are the measurements which work fine. On the top right, you can see another vendor at the plugfest. This is Anritsu, and one of the DNA measurement vendors at the plugfest who is doing some measurements. And the bottom right, you see Keysight DNA measuring passive devices with 2 fixtures attached to it. at up to 50 gigabaud. So I think this is a nice slide summarizing what you will see in the physical layer part of the plugfest. So imagine your device is plugged into this environment. All right, let's jump to the next slide. By the way, the whole test is done typically at UNH, so University of New Hampshire Interoperability Lab. That's the speaker, Kay, who is also the moderator. She's a representative of the IOL. And here is a picture of a fixture. I would like to give credit to the fixture vendors. If you bring to the plugfest your fixtures, this is very valuable for everybody. So typically we have several different vendors bringing it, and this one I would in particular like to applaud. Their contribution to the plugfest is invaluable. So thank you. And you can see from the logos who the vendor is maybe. So let's see, fixturing is necessary for most of the measurements, but some DUTs are measured at their test board. And so if you bring a non-fixtured test board with just SMAs coming out, that's also acceptable. And some provisions might be needed to make the measurements done without a fixture or without a connector to be completely compatible to the standard. And that flexibility is in place. Please, next slide. All right, here's a detail of the Tektronix station. You can see that there is one Tektronix AE running measurements on a dual stack of Tektronix scopes. In the background, you see two other Tektronix engineers working on another one. So again, you can have a better throughput with more scopes, and that's part of the plugfest. Additionally, some measurements are done on one station, some other measurements, let's say lower speed, might be brought up and enabled for testing on another station. Next slide, please. All right, so here is the point about the measurements at the test point. So John Calvin from my esteemed colleague from Keysight already pointed out the fixturing at TP2, for example, for the CR, and the way the fixtures let the user measure at the right point from the IEEE point of view. So fixturing, as long as the fixtures are valid, that is the right way to do these measurements. So what do you do if your DUT is a test board and doesn't have the connector shown on the left as at the MDI border, and does not have some of the loss between the chip TP0 and the connector at TP1? One possibility is to measure at this sort of TP1 SMA, if you would. Practically, it's a V connector, right? But a connectorized interface, and then incorporate the loss of a typical connector and a test board into your result in software. And that's important to emphasize that if you have a device without connectors, you need to do this step. Otherwise, TP1 results will be mostly optimistic. You will get slightly better results than you would get if you have the connector and a loss of the fixture. The standard expects you to measure at TP2, so the connector and the loss of the fixture are built into the results of the standards or into the compliance requirements by the standards. So if you skip that, you need to introduce that fixture back in, and you can do that by embedding in software on the oscilloscope waveform data. So please keep that in mind if you will be coming with DUTs without a full connectorization. If your DUT is a test board, for example. All right, let's go to the next slide. So a quick reminder of what is it the plugfest aims to test to. It's quite simple. We simply look up the compliance requirements from IEEE standard. In this case, is the AO2.3 CK, section 162. So clause 162 has, let's say, in this case, transmitter specifications. This is the first half of it. Another part of this table is below. We'll get to that in a moment. So we expect that all of these parameters can be tested in the plugfest. Ideally, test and measurement vendors show up with capable solutions which can go through this, and they will ideally all get the same results. So you'll find out exactly where your device is with regards to these compliance specifications. Now, in practical terms, there are some problems occasionally, and that's exactly what we have the plugfest for. If everybody is always passing exactly the same way in all the test gear, then probably the plugfest is just a rubber stamp for what people already know from their own labs. So let's talk a little bit about the more interesting stuff. What things could go wrong in the plugfest like this? Next slide, please. All righty. So I think the JIRA specification is a great way to start with that. So the clause 162 JIRA specification, this is bottom of the table you saw before, lists several of the JIRA specs. And you already heard my esteemed colleague from Keysight, John Calvin, discuss it. So let's add a little bit of the plugfest view and also some Tektronix comments on these measurements. So JRMS, J3U03, J3U, and even a JIRA peak-to-peak. Why are these specifications in the standards? Because there is a little bit of a overlap between especially the J3U03 and J3U. So in fact, the measurements on the 12 edges in the pattern are complex in that the edges are oftentimes hidden. So previous speaker already mentioned that the large transitions, which are labeled here 03 on the third row of the tables or second numbered row of the table, the J3U03, those results are easier to measure. Does that really mean that jitter should be less on J3U03 versus the J3U? Well, not really. The allowance for the J3U is really just the allowance for the measurement problem. So the standard body expects or understands that measuring J3U on a small transition, let's say from 0 to 1, is significant signal-to-noise ratio measurement problem. The trace has enough jitter and also, oscilloscope noise on it that the measurement is difficult to do. Besides just oscilloscope noise, though, there could be a problem in signal integrity of the whole system, which might be still passing on a receiver, but it makes the result hard to measure. For example, a reflection on the test fixture, on a compliant test fixture, could provide a double edge right at the threshold voltage. Where do you expect to measure the jitter? And the jitter will appear inflated. So the J3U seems like a relatively simple measurement if you would think of a clean signal, but in practice, and I don't mean a catastrophically hurt system, I mean a system which might be passing all the specs, that system still could have signal integrity issues, which make the J3U measurement much more interesting than we all wish. So let's discuss that. Let's discuss also the even odd a little bit more. And let's go to the next slide. All right. So the J3U is a measurement which, in fact, in the lab, you find sometimes doesn't work. That is, you can have a perfectly operating system, you can have a good fixture, you can have a good oscilloscope system, and you can still find out that J3U doesn't yield. What then? right? So one guide for you is the possibility of using the J3U03 as a first indicator if you have a problem or not. And the standard does give you value. So if you are passing J3U03, you might conclude that J3U is probably passing too. But you don't know that if the result on from the oscilloscope is impossible to get or it's inconclusive, not stable enough. So this is a problem for the industry. And the oscilloscope or the TNM interested parties are looking into that. Possibly we can bring up some measurement improvements that would make this measurement easier to do or more reliable to do. So if you run into a problem, I encourage you to discuss it with your oscilloscope provider. Don't just jump around and blame the setup or blame the measurements from the IEEE. The effort is by all parties a best effort we can do. But as the time goes on, we learn more about these problems, and we get better and better at fixing them. So what was really unsurpassable problem at the previous plugfest, in some cases already fixed at this plugfest. And before the next plugfest, I'm sure our results will be again more stable and more accurate, because we are trying continuously. Tektronix certainly is continuously to get these measurements, which are really hard, well, get them going. Sorry, there is a typo here. Why does the standard capture J3U03 as the mandatory? So the point is not that J3U is not mandatory. The point is that the J3U has a looser spec. Okay. Now let's talk a teeny bit about the EOJ. So the even odd jitter measurement is an interesting problem. So if you have much of a history behind this measurement, the even odd jitter, roughly speaking, is trying to measure if the last stage of the transmitter has a sort of two branches of an output max disparity. They are not the same timing. So this sort of disparity in output timing between even and odd is to be found in a fairly reasonable way. The trouble is that the measurement is not easy. So in fact, this timing of this pattern versus the jitter has been with us for a while. The PLL loop bandwidth at PAM4 at 53 gigabaud is 4 megahertz. And there is a suspicion that this is a problem on a pattern which has a similar repetitive rate. In fact, if you look at 25 gigabaud NRZ, so that was a quite older standard, you can see that there the PLL loop bandwidth was 10 megahertz. And similar problem didn't quite become important. So it's not completely clear to Tektronix that the bandwidth is the main problem. I would propose that the problem still needs further study. Anyway, IEEE did accommodate it in two ways, and one of them is lowering the PLL loop bandwidth, and that's a very easy thing to do. So I highly recommend that switching to a shorter pattern, PRBS9Q, is another approved method, and you are certainly encouraged to try all three. I think that it's important to keep track what your result is. If you are testing a part and your end user might end up repeating the tests, if they come back with a result, you want to know which method they used and what was the comparable result on your system. So please keep track of what loop bandwidth and what pattern you used, if you if you manipulated the pattern especially. Pretty much all the transmitter measurements done on CK are done with PRBS13Q. So that's the obvious pattern for most of us. And I would switch to PRBS9Q only if I am quite sure that I see a problem with the 13Q. All right. There is some possibility that the real-time oscilloscope really is the better tool for this. But I am, again, a little bit cautious on saying that we understand exactly what's the problem. We are quite comfortable that we are okay on Tektronix side with this measurement. So there is a little bit more on this in the future, hopefully. I think that's about it about these two complicated measurements. On the first surface of it, J3U should be a simple measurement. Again, it's convoluted. And the EOJ has a similar problem. There is a suspicion of this bandwidth trouble. And again, several things around it. I think that's most I had on the technical side. Let's go to the next slide. So speaking back again with the EA voice as an organizer of the plugfest, the Ethernet Alliance 100G plugfest measures specifications to IEEE AO2.3 specifications, and then also does an interoperability test. There is a very similar standard closely relating to the performance specs or the physical error compliance specs of IEEE, and that's the InfiniBand RoCE. The InfiniBand RoCE uses pretty much either the Ethernet PHY or near it. So since some of the measurements are the same or very close, there is a good opportunity for us to cooperate. And indeed, we already did that at this last plugfest. So in the case that you have interest in both RoCE and IEEE, definitely do mention it to both the EA contact you have for the next plugfest, and also to the InfiniBand contact you have for RoCE or whatever. And we are planning to widen the cooperation as makes sense in the future, so as to avoid duplication and sharing efforts. That's that. Hopefully we will see you at the next plugfest, whether it's second half of 2023 or next year. Thank you. Okay, back to you.
Excellent. First off, just want to thank all of our panelists for putting their time together to put together the slides and share their knowledge with us. We do have just a couple of questions that we're going to get through. We'll get through as many as we can in the next 10 minutes, and then any that we don't get to, we can follow up with after the fact, or if you come up with any after the fact, please feel free to reach out to us. We can certainly work on getting you those answers. But actually, with the first one, I'm going to dive in a little bit right off of what you were mentioning, Pavel. Looking at the plugfest, and of course the IOL is happy and looking forward to hosting the next one. But what's the next one going to be on? What's going to happen? And if somebody does want to get involved, how do they get involved in the entire plugfest process?
So to answer that question, please just simply contact the Ethernet Alliance. There is a website, find the website and talk to us. You can contact any of the presenters on today's webinar. Obviously, we are all part of Ethernet Alliance, but I would recommend the best way is just contact EA directly. Ethernet Alliance website is mentioned at the bottom right of this slide. And talk to us and let's see what we can do next. Thank you.
Sounds good. So I've just got a couple of questions. I'm going to pass them to individual people just to get us started, but please feel free to tag in the other panelists as you see fit. So I'm going to pass this one to John first. So talking about you were mentioning some of the mated test fixtures. What happens if the loss that we have kind of falls out of that allowable envelope? Can we just de-embed the losses to bring it back in spec, or is there something else that can be done?
Yeah, that's a good question, Kay. You know, the loss profiles are given upper and lower bounds for good reason. And if you exceed those limits, then the temptation would be to apply some sort of de-embed function to pull the losses out, either to increase them or to decrease the losses. With relatively few exceptions, I think V sub F is one of the exceptions. You're not allowed to do any kind of de-embed. And the reason for that is the following. If you de-embed typically follows a zero forcing function, where you actually are providing gain to compensate for additional channel loss that you might have to compensate for. And that zero forcing function tends to increase your JRMS value. So your jitter goes up. So while you might actually get a passing J3U number, your JRMS number is now failing. So it's a zero net gain where you push on one aspect of this and it exceeds spec somewhere else. So if you want to do de-embed, I'd be careful to de-embed to the spec limits and no further than that.
Awesome. Thank you for that. I think I'm going to pass this one to Aditya, just looking at what are some of the different, I know you mentioned a little bit of the 400 gig, a little bit of the 800 gig, but what are the different variations of Ethernet at the 400 gig and kind of where are we at right now?
Okay. So in terms of the 400 gig Ethernet, from a design perspective, we can have like different variants. It could be like 16 lanes of 25 gig per lane, which is running at NRZ modulation, or it could be 8 lanes running at 50 gigabits per second per lane in PAM4 modulation. And the third is the 4 lanes running at 100 gigabits per lane with, again, the PAM4 modulation. And in terms of the transceiver form factor, it could be like a QSFP-DD or an OSFP or a CFP8. So these are the different form factors the Ethernet variants could be. And again, as we discussed earlier in the session, we have this copper and opticals. And again, there are deeper divisions under the hood as well. So this is pretty much it.
Awesome, thank you. I'm going to pass this one to Nathan. We've seen with, cables, we see them short and long, but are there any specific length specifications for copper cables that are designed to operate at that 100 gigabit per second?
So great question, Kay. Generally, the way the standard is around loss and so the objective when we set off to write the 802.3 CK spec was to aim for 2 meters of reach for a passive copper cable. And of course, there's a lot baked into that. There's an agreement on how much loss the host is going to have, the connector loss, et cetera. As I mentioned during the presentation, as the capabilities of the silicon improve over time or next generation silicon processing nodes are brought to bear, then we might be able to see the ability to increase the reach of those cables. And we're right on the cusp of seeing that now. So there's some next generation switching silicon beginning to come to market where we're seeing the ability to provide a totally compliant electrical performance over longer reaches than here. So a 3 meter, I think, is something that's validated as far as unofficial, but we've even seen some lab measurements where we've gone as long as 4 meters and gotten compliant results. So it does change with time, but generally speaking, yes, it's based on an overall loss parameter, and for that cable assembly mated to those 2 MCBs, that parameter is 19.75 dB. So that is the spec. But over time, as transmitters and receivers improve, then they can tolerate increased numbers beyond that.
Sounds good. We'll look forward to seeing if those transmitters and receivers can continue to stretch that reach out even longer. So I think we've got just a few more minutes, so I think we'll be able to fit in just one more question. Passing this off to you, Pavel. So I know this webinar was focused really on the 100 gig per lane technologies. How does this really relate to these 800 gig, 400 gig technologies that we're hearing that are coming out in the future?
All right, nice question, thanks. The 800G is a funny number, right? Because if you look at the IEEE documentation, the standard for 100 gig per lane has 400G, which is 4 lanes, 200G and 100G. It does not have 800G. So is it really a standard? So you can look to MSA, such as the documents for OSFP modules or QSFP DD modules, where there are more detailed specifications for the 8x version of this physical layer. So you get 8x100. You can look to the specifications in the MSA documents. And those are easy to download from OSFP website or QSFP website. The thing is, they are relying on the physical links from the IEEE AO2.3CK. So in fact, the specification is from IEEE. There is a difference maybe for the 1 lane, but otherwise you have multiple lanes. The spec is not really significantly impacted, whether it's 2, 4, or 8 lanes. In the future, we will see more higher speed, and we might also see more lanes. 16 lanes is not unheard of, and it has many difficulties, but it can be done. So you are looking forward to 1.6 tera, 3.2 tera standards for the IEEE standards. Thanks.
Yeah,
Perfect.
and I would just add on to Pavel's comment that IEEE actually does have a project in process right now, 802.3DF, which is addressing 8 times 100 gigabits. So that is progressing nicely and will be coming to market in the future.
Excellent. Sounds like the perfect place to wrap us up. So thank you everybody who was able to attend the event. The recording will be sent out afterwards to those who were registered, or you'll be able to, if you need to share it with colleagues, you'll be able to share the links to come back and get the video on demand. But other than that, if you have any questions, please feel free to reach back out to the Ethernet Alliance. Otherwise, thank you again from the panelists, and hopefully we will see you all at another event very soon in the future.
Looking forward to it. Thank you.
Have a great day, everyone.
Thank you.
Thanks all.